Okay, we understand what the downsampling operation does in time domain. We also understand how does the downsampled signal look like in relation to the continuous time signal that we further downsampled. In particular, recall that when we have the following block diagram, we have a signal xn that we downsample by a factor of m to get xd of n, and xn is related to an underlying continuous time signal. So xn was obtained in the following way. We sampled every t seconds. When we have that, then we know that the DTFT of our downsampled signal is related to the original continuous time signal as follows. We have multiple copies, we have scaling of the amplitude, and we have scaling of the frequency axis, and so forth. So this is what we understand. The question is, do we always have to go back to the Fourier transform of our continuous signal for finding the DTFT of our downsampled signal? So the question we want to address is the following. Is there a direct relationship between the DTFTs of xn, which we will denote by x of e to the j omega, and the DTFT of xdn, which is this xd of e to the j omega? And the answer to that is yes, that is true. And the focus of this lecture is to figure out how we derive that relationship. Okay, now in order to do that, we look at the above expressions star, and then we replace the summation in that expression by a double summation. So how do we do that? Well, in order for that, what we do is we write k equals I plus Lm, where I is an integer from 0, 1 up to m minus 1, and L is an integer from minus infinity to infinity, both integers. So let's convince yourself that it is the two are equivalent. So as L goes from minus infinity to infinity, we are looking at multiples of m, and then within those multiples of m, we also add I from 0 to m minus 1 to actually cover all possible values of k between minus infinity and infinity. For example, when L equals 0, then I have I ranging from 0 up to m minus 1. I cover k equal to 0 up to m minus 1. When I have L equal to 1, I cover k. When I vary I cover k from m up to 2m minus 1, and so forth. So once we are convinced that this one index can be replaced by two indices, then we can write rewrite star as follows. We have xd of e to the j omega. Everything else is the same. The only thing is we are changing the summation. So one summation goes from I from 0 to m minus 1. The other goes from L from minus infinity to infinity. The rest of the thing I'll keep the same, and then instead of k, I replace that with I plus lm. And then I have empty in the denominator. So what I'm going to do next is simply break down a few things. First of all, 1 over m, I'm going to bring 1 over t inside the summation. I'm going to write this 1 over t, L from minus infinity to infinity, and then I'm going to break this 2 pi I plus lm as follows. I'm going to write that as 2 pi I over mt. I'm going to break that minus 2 pi L. M will cancel. I am left with t. This is the next expression that I have, and I'm going to call that double star. Okay, now to derive the relationship between the DTFT of xd and the DTFT of xn, let's recall that since xn comes from sampling x of t, we know, so we have a similar relationship between the DTFT of xn and the continuous time Fourier transform of x of t. What is that relationship? Similar as above, it is 1 over t, because the sampling time for that case is t. I'm going to use L instead of k because it's just a dummy variable. X of, okay, I'm missing j over here. X of j omega minus 2 pi L over t, which is equivalent to 1 over t summation L from minus infinity to infinity x of j omega over t minus 2 pi L over t. Okay, I'm going to call this 3 star. So compare now, compare this boxed expression in star, compare this with 3 star. So compare the box expression in double star with 3 star. So compare in star, or rather double star, and triple star. What we notice is that the box is simply equal to x of e to the j omega. So box in double star is simply equal to x of e to the j omega, with omega replaced by omega minus 2 pi I over m. Okay, so let me actually erase this box to avoid confusion. And let me say that compare box in double star and this quantity. Okay. So what we see is that the box in double star is simply x of e to the j omega, but I am replacing little omega with little omega minus 2 pi I over m. So I just plug that into double star. This means that xd of e to the j omega, this is going to be equal to 1 over m summation I from 0 to m minus 1 x of e to the j omega minus 2 pi I over m. So this is the relationship that we were interested in deriving. This is the relationship between the DTFT of my downsampled signal and the DTFT of the signal that I started with. So I now no longer need to actually think about the continuous time signal. I given a discrete time signal and its DTFT, I can actually compute the DTFT of my downsampled signal. Now let's stare at this boxed expression to figure out what is it telling us. So there are three things that happen in the frequency domain during downsampling. And those things can be viewed from this box expression. What are those three things? The first one is that when we do downsampling, there is a scaling of frequency axis by a factor of m, and that is due to this capital M here in the expression. We have a scaling of frequency axis by a factor of capital M. The second thing is that we have a scaling of amplitude by a factor of 1 over m, and that can be seen here. We have a scaling of the amplitude of DTFT by a factor of 1 over m. And the last thing is that we actually get m copies. So this is due to this summation. We get m copies of the frequency and amplitude scaled versions of my DTFT that are shifted by multiples of 2 pi. So this is because of minus 2 pi I, this is the shifting operation. So we get shifted copies, but now we get only m shifted copies, not an infinite number of shifted copies that happen when we go from continuous time to discrete time. So this is the mathematical expression. Let's take a look at a couple of examples, graphical examples, to better understand how does this relationship that we have in the box plays a role in the DTFT domain exactly. So let's take a look at this example. In this example, we are given a discrete time signal whose DTFT is this of this form. The maximum height that it attains is a, and the periodic repetition of this DTFT, it starts from minus pi to pi and it keeps on going. Now we want to look at what happens when xn is downsampled by a factor of 2. What happens to the Fourier transform of my signal? So the first thing that happens is we are going to get 2 copies. So let's first focus on the first copy. The first copy is going to have the frequency axis scaled by a factor of 2, and it will not be shifted. It will start from 0, and the magnitude will be scaled by a factor of 1 over 2. So what is going to happen because of this scaling is that the pi region, pi frequency will go up to 2 pi. So this a will become a by 2. So we'll get, let's say this is a by 2, and this is my region from minus pi to pi will get stretched to minus 2 pi to 2 pi, and then at 4 pi and minus 4 pi I'll get this further stretching. So this is now whatever was at 2 pi is going to happen at 4 pi. Whatever was at minus 2 pi will happen at minus 4 pi. So I have further stretching. And similarly over here. So this is due to the main copy that I have. Okay. Now this is just one copy. I have to have, if we go back and look at the expression, right, I have two copies of this because summation is from 0 to m minus 1. So I need to have one more copy of this same thing. I have to have one more copy of the same thing, but now shifted by a multiple of 2 pi. So what would that look like? Okay, that will be starting, so this whole thing gets shifted by a factor of 2 pi. So I'm going to use a different color and try to make it similar shaped. So this is what the other copy will look like. It has been shifted to 2 pi, but other than that, it has exactly the same shape. And so forth. So what will the final Fourier transform look like? Of course, you have to now add both these copies up. And if you add both these copies, actually what you are going to get is this straight line, because everything is going to get added up. Okay. So what has happened here? Your final Fourier transform is this straight line, which is xd of e to the j omega. This black curve was due to m equal to 0. The dotted blue curve is due to m equal to 1. The final one, the summation, is this straight line. And why that has happened is because this is effectively the aliasing effect. You see, our x of e to the j omega was not band limited to pi by 2, which is the requirement that we saw earlier, that we must have signals that are band limited to pi over m to avoid aliasing. This is that aliasing effect showing up in discrete time. So this is the case when we had aliasing. The discrete time signal was not band limited to pi over m. It is also important to point out that where these different copies intersect with each other and cause aliasing is precisely the frequencies pi and minus pi. So once our main copy expands beyond pi and minus pi, it's bound to lead to aliasing. Let's now look at another example. This is an example where we want to do downsampling by a factor of 3, and our original sequence is band limited to pi over m, which is equal to pi by 3. And let's assume that this is the Fourier transform of my original sequence that we are downsampling. So now what happens to our downsampled version? So the first copy will basically scale your Fourier transform. So whatever is between minus pi by 3 and pi by 3 will get stretched to minus pi to pi. The height will get stretched to a by 3. Now this frequency 2 pi will go to 6 pi, which we don't have room here to display. This frequency minus 2 pi will go to minus 6 pi. So you now have the main copy goes from minus pi to pi, and then there is a gap till 5 pi. So what fills that gap? Well, the same copy will be shifted by 2 pi and 4 pi. So there will be a shifted copy at 2 pi. So when we shift this copy at 2 pi, we will get this thing. This is due to the copy of this thing shifted by 2 pi. And we'll have another copy that will be shifted at 4 pi. So that copy will appear over here, and that will go up to 5 pi. Height of all of these things are a by 3. Now remember that I had said that this 4 pi, this minus 2 pi got shifted in the principal version to minus 6 pi. So when we shifted that principal version to 4 pi, this minus 6 pi will actually also get shifted to minus 2 pi. So we get this thing. So basically, one version of the whole shifted spectrum is this blue thing and this blue thing. And this blue version is due to I equals 2. Now this red version is at 2 pi. Again, so when we shifted minus 6 pi, we'll get minus 4 pi. So this is my second version of which is due to I equal to 1. So just to recap, when we have m equals to 3, we get 3 summations in our formula. We get 3 copies. The principal copy, which starts at omega equal to 0, is at 0, and then at 6 pi and minus 6 pi and so forth. Then we shift that thing to 2 pi. When we shift that to 2 pi, we get this red version at 2 pi and this red version at minus 4 pi. We shift that further to 4 pi, and then we get this blue version at 4 pi and then this blue version at minus 2 pi. Now if you look at this expression, actually there is a short way of actually getting to this final graphical representation. What is that short version? Well, instead of looking at or adding 3 different versions or m different versions, all you could have needed to do was actually just stretch whatever is between minus pi and pi, stretch that out by a factor of m, in this case 3. So pi by 3 goes to pi, minus pi by 3 goes to minus pi. In the previous example, it was already at pi, it went to 2 pi and minus 2 pi. Once you stretch that out and you scale the amplitude by 1 over m, once you do that, actually, you can just do a periodic repetition of that for every 2 pi interval, and you will get back this plot. So you don't actually need to do all that summation. That's sort of a direct way of actually getting to the same expression. Now, if your original Fourier transform between minus pi and pi did not satisfy your band limit constraint, then what would happen is that this black version will extend beyond minus pi and pi. But when you copy it, that's fine. When you copy that to 2 pi, you will get you'll get an overlap, and that's where you will get aliasing. So if we were to go back to what we saw earlier, we could have again done the same thing. We just stretch it by minus 2 pi to 2 pi. Then we copy that whole thing to 2 pi, and since there is aliasing, we add that up. So these are 2 examples to clarify what is the frequency domain relationship between your downsampled signal and your original signal. And to derive that relationship, the mathematical expression is given by this formula. And this expression actually does not involve any continuous time signal at all. So if you are given a sequence and you downsample it, knowing the Fourier transform of that sequence, you can go to the Fourier transform of your downsampled sequence. You may or may not have aliasing depending upon whether your original sequence was band limited to pi over m.